So I can hear that not only is some wind rustling sound is coming through in the recordings, as usual, the cold La Nina winter continues here and nice breeze, cool breeze is occurring, but also the building is testing out the fire alarm, so I hear some of that being recorded as well. Hopefully it's not too bad and the records are clear enough. So we touched on grids, staggered grids, A grids, B grids, C grids, E grids, and so on and so forth. Let's just look at it a little bit again with the nicer pictures from David Neelan's book. So here again we are looking at longitude, latitude grid in pressure, and we are looking at some topography and typically how grids are stacked and how variables are staggered. So you have volume quantities like pressure, temperature, humidity at the middle of the grid, and then velocities at the edges, so on and so forth, so that you can write the fluxes in natural forms. Typically fluxes are like u dt dx, u du dx, and so on. Of course, when you write u at the edges, then u du dx, u dv dy terms become a little bit more complicated as well, as we saw before. So this is a section of the grid for a typical atmospheric general circulation model. Grid would continue globally, so you can imagine the sphere on which this is put. The atmosphere is divided into a finite number of grid cells in the vertical and horizontal. Dots indicate vertices of grid cells. The levels in the vertical are of a variable spacing and are usually in a modified pressure coordinate that follows large-scale topography. So there are ways to define pressure dependence with altitude to make the grid resolution resolve those processes better. So you can see that the resolution of the lowest grid here is different than here, for example, and these grids here are placed more closely here than here or here. So there is ways to account for pressure variations at the surface and processes that are dependent on those pressure variations as well, by making these higher resolution. A particular level broken out in form A, horizontal grid size corresponding to longitude and latitude is indicated by delta x and delta y and delta p in the vertical, while without topography is delta p. Transports or fluxes into and out of a particular grid cell in both horizontal and vertical. Again, just reminding ourselves of what we did. There is the fire alarm which is coming right through my recording. It's been going on for days, so I cannot really wait it out. A vertical column showing two examples of parameterized physics of small-scale processes within a single column. For reason, I hate it. Okay. A moist convection is shown here in terms of the actual process. Clouds are shown schematically with convective updrafts, not to horizontal scale. Obviously the vertical scales are greatly exaggerated with respect to the horizontal scales. You can imagine that the convection is typically happening on a very small scale. The fraction of horizontal area of the grid cell that each cloud would occupy is about 0.0001. So they are tiny features, which is what makes modeling them even harder, but also that also allows us to take the very strong vertical motions in those convections and remember that the large scale environment remains basically in hydrostatic balance. The individual clouds are not calculated, but the average of all the updrafts in the domain is parameterized as a function of grid scale, averaged temperature and moisture. So there are ways in which to take the explicitly predicted temperature and moisture. Remember, those are prognostic equations, dt, dt, dq, dt, and so on. And you can compute instabilities in the vertical using moist static energy and so on. And then you can parameterize updrafts that are driven by large-scale circulation, vertical instabilities, and so on. And then B, there is radiative transfer. The infrared emission, it wiggly arrows from a single layer. So we are here with a layer reaching its temperature and receiving energy from below and radiating energy down and up. So each layer is doing that, and some of it may go all the way out to space, and some of it may get trapped in one layer or the other in the vertical. So this is a complicated calculation. In fact, in the atmospheric GCM, radiative transfer calculations are the biggest part of the computational cost. So infrared emission, wiggly arrows from a single layer is shown affecting other layers and the surface where absorption occurs. Emission from the surface that is absorbed in the layer and emission from the layer and the uppermost layer to space are shown. Emission and absorption at every layer interact with all the other layers. So we did simple averaged one-dimensional energy balance calculations and wrote a model and did many calculations with it. But in a GCM, this happens in each grid. We are only showing a small chunk here, schematically showing a mountain, but obviously the resolution would have many grids here, or many hundred grids, depending on the resolution. So these are all very complicated calculations, and that's where a lot of the uncertainties and biases come from as well. To look at the topography of the North America shown at two different resolutions. This is resolutions. This is of course at a very low resolution, showing grids in the vertical and horizontal. So we are just showing one direction, but there are also multiple directions involved here. So this is a 2 degree by 2 degree grid typical of climate models. So most global climate models are run at such resolutions, even though with growing computational power, intrinsic resolutions are getting better now, down to 1 degree or so. 2 degree by 2 degree typically corresponds to 200 kilometer by 200 kilometer, which is very coarse when you think about the processes that happen on small scales and so on. And it also tends to smooth out the orographic features and other features that we have to represent. So this is the US with its mountain chains. Here is Florida, here is Cuba, so you can see how grid points are smoothing out all the features. But when you have much higher resolution, 10 times higher by 0.2 degree by 0.2 degree, then you can zoom in and see how much better the representation gets of the coastline, of the orographic features, of the transition between land and ocean, and so on and so. This is the Gulf of Mexico, for example. So obviously higher resolution is better just simply for representing the features which obviously will affect the circulation and the orographic rainfall and so on, windward, leeward circulations, waves generated by the mountains, and so on and so forth. But parameterizations have to also worry about what is being represented at different resolutions. So there is some adjustments, even the mixing and so on often tend to depend on the resolution. So all those kinds of details have to be worried about by the modelers. The computational time, of course, is related to the computer time per operation. Any x times y, x plus y, and so on is a operation, and there are a number of operations per equation and number of equations per grid box, because on each grid box you are solving number of equations like momentum, energy, continuity, water vapor equation, and so on. And number of grid boxes, which depends on the resolution as we see here, and number of time steps per simulation. So when we are discretizing dt, for example, how many time steps are involved in integrating for an hour, for a day, for a season are going to determine the computational time. So obviously this is a very heavy cost as we increase resolution. This is going from 2 degrees to 0.2 degrees, so that's a huge jump in these things. And then imagine adding chemistry, adding other details like land vegetation equations and so on and so forth. That makes it very expensive. Okay, so in the ocean, longitude, height, cross section through an ocean model grid, vertical scale is stretched in the upper 500 meter of the ocean so that closely spaced levels near the surface can be seen. The solid curve gives the true bottom topography, and the dark shading shows the model approximation to the topography. So the real topography is shown in this black line here. The model resolution is shown with these X or Y direction. So here is the, let's say, X direction, Y direction, or X direction and Y direction, and you have the vertical grid here. Near the surface you have these processes that are important, so we tend to increase the resolution near the surface to account for various processes. Also they could be increased near the grid is shown by changing the grid spacing here just to illustrate the problem. So you have atmospheric orography here, ocean orography here, and you always have coastlines, exchanges of energy, matter and water at the continents. And when you do coupling, you have to worry about winds blowing over the ocean versus the land, heat flux over the ocean versus the land, evaporation and precipitation over the land and the ocean, and so on and so forth. So the coupling is typically thought of in a simplistic sense this way, where you have a GCM talking between atmosphere and ocean, and also land and atmosphere in terms of sensible heat, solar radiation coming in, long wave radiation going out, and also back radiation coming from the atmosphere to the ocean. Some of it penetrates into the ocean. Ocean has mixing and currents and winds, obviously from the up, let's say above 10 meters to the surface. Because of the friction, they decrease and hit the water and push the ocean and create currents. So momentum penetrates into the ocean. As you can see, the currents decaying from the surface to the depths. So there is turbulence, heating, cooling, freshwater exchange happening at the surface, which are typically represented by increasing resolutions. There are also processes that are special to the equator, so meridional resolution also can be increased around the equator, and so on. You also have to, of course, prescribe land surface types following biosphere atmosphere transfer schemes, which include things like ice cap, tundra, bog, mixed woodland, evergreen, deciduous, and so on. Getting data at high enough resolution to prescribe them is hard enough, even if you want to use them as fixed in time, which is not accurate. And then if you want to do dynamic vegetation, where vegetation actually changes seasonally and interannually, and maybe in terms of response to global warming and so on, then it becomes really much more complicated. But most typically the land use types are prescribed, and the simulations are carried out at least for short periods. That's not a problem. But now more and more IPCC models have dynamic vegetation, which are represented in various functional types that depend on precipitation, temperature, humidity, and they also compete with each other, and so on and so forth. And they vary from tropics to the high latitudes in terms of rainforests, temperate forest, boreal forest, tundra, and so on. So the realism is increasing, especially for allowing feedbacks between vegetation, albedo, evapotranspiration, energy exchange, and atmospheric response, and runoff into the ocean as well. The hydrology is also affected by the vegetation dynamics, root dynamics, and so on and so forth. So these details we didn't discuss in the first part with Tom Stoker's book, so I just wanted to include that here as well. Okay.